universal guidance to whatever physics you want to do. Source and sink. And then that gives you the time rate of change of your thing. Even in economics, in the finance, let's say the government, its annual budget, same thing. You have source, you collect all the tax from everybody. You have source. Then you have the sink. You use it out to construct highways and so on. And that gives you the rate of change of your budget. Just that simple. Okay. Now, so this is governed by what's called realization time of matter, because you are exchanging energy. Now, as xe becomes small, it increases, and energy transfer becomes less effective. Now, those small fractions, this fraction of the electron continues to occur with photons, right? Now, the electron mean free path is much smaller than the photon because you have way more photons, 1 billion times more. So this electron, unfortunately, just keep on hitting photons and do this Thomson scattering. Whereas photon, the pure photon, each one can only hit this electron once out of 1 billion. So you have 1 billion photons waiting around, but on the average, your particular photon, you're watching that particular photon, its chance of hitting this electron is only 1 10 to the minus 9, right? So photons mean free path is way lower than the electron mean free path. Now, so electrons mean free time is way shorter than the photon mean free time by this ratio. Okay, and combining this with what we had in the previous page, you find this. So this shows you that electrons are tied to photons until the goes down to about 20 or so. This conclusion is a little bit of a jump, but it is true. So even down to Z about 20, you're still having a little bit of this interaction. All right, for the remaining time, let's talk a little bit about baryogenesis. That's yet a very important aspect of our universe. But that's involving entirely different physical considerations, unlike what we just now talked about. Because just now we were talking about mostly based on our standard model of physics, electrons, protons, neutrons, and things like that, whose interactions were pretty much well known. Okay, but this baryogenesis is still, down to now, an open question. If any of you are interested at all, this is a direction where you can do some research on. Now, in our discussion, up to now, you have heard me talking many times about photon to baryon ratio of 10 to the 9. And that was confirmed, for example, by BBN, abundance of light elements, and things like that, right? Now, since baryons and antibaryons will annihilate when the universe cools down, down. Well, when I say flying all around, I wish you remember what I said. It's, for example, if you have a proton, you have also antiproton. When they hit, what happened? They turn into energy. They disappear, right? Matter and antimatter, when they hit, they disappear. But when the universe is very hot, let's say P plus P bar turns into 2 gammas, 2 energetic, huge photons. Now, at that second, they whoa, this universe has 1 proton less, as well as 1 antiproton less. But don't worry, the universe is so hot with all the high energy photons and so 2 other photons, when they collide, can turn back into proton, antiproton. Likewise, electron-positron pairs can annihilate into 2 gammas, but 2 gammas can return you the favor, turn into E plus E minus. So that's under the very early universe. Now, but if there's exactly the equal number of like the protons and antiprotons, then as the universe cools down, they should annihilate entirely away. When their kinetic energy is not high, can I imagine that? Let's imagine that our universe, what's the rest mass of a proton? What's the rest mass of a proton? 800, 936. Yeah, maybe something like that. Near 1,000. Usually we say 1 GeV, roughly. Now, imagine your universe, the universe is already cooled, so that the photon, background photon temperature is much below this 1 GeV. Let's say 1 MeV. Then, when proton and antiproton hit each other, turn into 2 photons, each one with 1 GeV. But this is very rare in the universe, you know. And to have 2 photons from the background to hit, you know, with 1 MeV, let's say 1 MeV temperature at that time, it is impossible to recreate proton and antiproton. You need at least 2 GeV in total energy from the 2 photons to recreate proton and antiproton pair. So, as soon as the background temperature is below GeV, you cannot do the reverse process. Only one-way traffic. Now, if then proton and antiproton have the same density or the same number, they all annihilate away, then we won't have anything left. Okay? So this is a mystery. So why should there still be protons or baryons at all? So the inevitable conclusion, what's the meaning of this word in English? What's inevitable?
You can.
Unavoidable.
Yeah.
So the unavoidable conclusion is that the universe must begin with a slight matter-antimatter asymmetry. Now at high temperature, there must be slightly more 10 to the minus 9, 1 plus 10 to the minus 9 protons for every antiproton. Now, I think have I mentioned this to you? Our present observable universe, let's call it, Hubble radius. Within this Hubble radius, we find 10 to the 90 photons. How do I get that? You know how to get that? Each cubic centimeter centimeter of space in our universe has about 400 CMB photons. And what's the present Hubble radius? How big is our universe? Anybody?
70.
Say it again.
70.
70 what?
Um,
半天。So we have our present. This universe maybe we don't know what's out there, but let's say there's a Hubble radius. How big is it? If I were you, I'd just quickly wiki. That's it. Huh? Give me the number.
14.4 billion light years.
I want length.
13.7.
Yes, but light year, you translate it, I mean, I want length. How long is a light year? No, light year is a unit of length. What is a light year? How long is a light year? 你就把一年的秒数乘上光速不就了了吗？ How long is it? How many seconds is a year? Wow. How many seconds are there in a day? 86400不是吗？ Take a round number. So it's like 100,000, right, per day, which is what? 10 to the 5. Okay? 360 is 10 to the 2, roughly 3 to the 2. So together it's 3 10 to the 7. This is, you always have to remember, a year is roughly pi times 10 to the 7 seconds. Pi is a very useful number. So just throw it pi 3. 3 times 10 to the 7. How fast is the speed of light? 3 times 10 to the 10, right? Centimeter per second. So together is 10 to the 18. 3 times 10 to the 10 times 3 times 10 to the 7. Well, 3 times 3 is 10. So it's another 10. So 10 times 10 to the 8, 10 times 10 to the 10, 10 to the 7. So it's 10 to the 18. So a light year. Okay, light year. 10 to the 18 centimeters. And just now you guys told me how many light years is the Hubble radius?
14.4.
Yeah, let's now worry about point. So 14 billion. A billion is 10 to the 9. So this is about 10 to the 10, huh? Times 10 to the 18. 10 plus 18 is 28. So this is about 10 to the 28 centimeters. Is that okay? So this is our kindergarten, I mean, but you don't even, after this course, you cannot even tell people quickly how big is our present universe, and that's it. So 10 to the 28, that's cubic, because we care about the volume. So cube is how big? Huh? 84. 84. So this is, the volume is 10 to the 84. Yeah, I think 85. There's a 3 pi over 4, or 4 pi over 3, I forgot. So about 10 to 85. I missed this point, 40% here. So 10 to the 85. Now, each cubic or centimeter cube. Each centimeter cube has 400 CFD photons. So, number density of photon, 400 per centimeter cube. This time this gives you times volume is the total number of photons. 10 to the 87. Yeah, I used to get 10 to the 90. People usually say 10 to the 90. Yeah, it's a 4 here, some cubic of 1.4. But anyway, around 10 to the 90. And you check through all the shiny things, galaxies and so on, it's 10 to the 80 protons. For example, the sun.
How could one count the number of photons within a certain volume?
Oh, because you know its temperature, and once you know its temperature, you know.
There may be little variations due to the fact that photons are massless, so it can be created.
Say it again.
I mean, photons are massless, so they can be created without nothing.
But didn't I say already that ever since the decoupling time to now, the photons were frozen? Those background photons never collide. Knight and Thomson scatter.
Oh, so they will be created in pairs. Oh, will they? Will they be created in pairs?
By what?
By inserting energy inside a small volume. They can be created. I mean, the single photon state is not a well-defined idea, because we cannot count the number of photons, can we?
Well, we can count the number of photons, but they are not conserved quantity, which I agree.
Yes.
But if after all these hours you are still not having this question, that means that I did not succeed in teaching. I repeatedly explained that, and that's why we spend hours. We're talking about down at some point in the history of the universe, the photons were freezing out. They are frozen out. They decouple from the matter. Those photons. Now, locally, you're right. Every star, every something, even our kitchen and so on. You should be able to create some photons that happens to be at the same frequency. Let's say what's the frequency for it? It's microwave. 2.7 degree K corresponds to some microwave. The wavelength is about a centimeter, maybe a little shorter, millimeter. Those photons are the present wavelength. That is about the wavelength of the present day CMB photons. You can, in principle, indeed, there's no conservation for photon numbers. So you can produce some at your home, somewhere in the galaxy. But to be able to create enough so that in every centimeter cube, you add some more to it. In the whole universe of that big, That's near impossible.
Oh.
You are really making a teeny tiny perturbations to that huge reservoir. You know, we already say there are 10 to the almost 10, a billion times more photons than electrons. So if you rely on your poor electrons to create a few photons, that wouldn't create any dent. The overwhelming majority of those photons were just, you know, untouched. Untouched. You know, this universe has so many billions of stars. Each one can create a little bit of these. Doesn't help. Doesn't help. You're asking a very good question. That for a ordinary physicist without much knowledge about cosmology is understandable. Yeah. But the amazing thing about this universe is that it's so vast. Okay, it's beyond our ordinary experience. You know, I can create some new photons for sure. You know, I can have a microwave oven. I keep generating 2.7 degree K photons out. I can do that. But you cannot beat, you know, 10 to the 80 and 10 to the 90. It's a huge difference. Yeah, I don't think you can ever be able to create enough to make any change. And indeed, you know, when scientists went out and measured the CMB photons, and it was, you know, this is 1992, like the Kobe experiment. They measured the black body spectrum. It was almost the best Planck distribution you can ever imagine in the whole universe, in all the physics laboratories. It's almost exact. You don't even see error bars. It's just right on the top because the accuracy is way beyond the thickness of your curve.
So even the photons created by suns can be seen as small perturbations.
Tiny, teeny.
Oh.
Right. Yeah. So that's the amazing thing about the universe. You know, we said, I remember I asked you guys before, how many protons are there or baryon, you know, protons plus neutrons in the sun? Do you guys remember? Have I ever asked you? These are simple numbers. You know, I love to play with numbers. 10 to the 56. 10 to the 50. 51. Well, 50 something. Maybe 56. Now, you say, wow, a huge number of photons. 10 to the 56. And can I imagine what kind of numbers can be that big? Now, you say, well, but our galaxy has, you know, 200 million stars. Let's say on average it looks like our sun. So 200 million is 10 to the 11. Let's have 10 to the 56 times 10 to the 11. So 56 plus 11 is 67. Huge number. Now, but how many galaxies do we have? 10 to the 10 in this one. So 67 plus 10, 77. And just now we said 87. All the protons add together. It's tiny amount. Okay? Baryogenesis. Too bad we ran out of time. Maybe we should start from here on the next Sunday. And let's begin at 9:30. Alright, 9:30. Yeah. Sorry again that I was a bit late, but I tried my best. Because I have businesses by Friday, and the only way I can come back is to leave Paris on Saturday morning. And yesterday, actually, I wasn't in Paris, I was in Munich. So I had to get up at 4 o'clock and took a early flight to Paris from Munich to Paris and then fly back. So, so that's my life. Okay, all right. So see you next Sunday. Any question for me? I think you asked a good question in the sense that, you know, very often it's a little bit kind of go against our common sense, right? And so it's good not because anything else, but the rest may have the same wonder. And so after answering you, I'm letting all of you know that this is a huge reservoir of photons in our universe. And we are just kind of tiny dots. Okay, all right, great, thank you guys. Yeah, so that's it for today.